In this video, I will introduce you to the ability of the Fracture Surface Analysis Toolbox for Matlab FSAT to analyze the roughness of a fracture surface, so just a single fracture surface. As you have already known from the other videos, there were different steps in FSAT to complete the analysis. And the first step always has been the generation of the metadata. So again, you can download FSAT from the GitLab repository, unzip the file, and then you should look at first at the script generate metadata. It is documented script with a lot of examples of the different test cases you can run, which are also provided with FSAT. And in this case, we will take a look at the case B, as it's called, so single fracture surface. I just copied those from the example file generate metadata to another script, which is a bit shorter, where I only accept those parts of the script that are relevant for a single surface. Most of those metadata that needs to be provided here is, or should be already available to you if you have watched one of the other videos, especially the one for analyzing a single height profile. So again, you have to specify a different case beginning in the first line. For a single surface, this is the case B, as was labeled. We want to have figures outprint, which is a PNG file format, providing name, path raw data, path where you want to store the results, delimiter in those files, the units, the cutoff values now in X, so in horizontal, and in Y direction, so in vertical directions. A similar function as they have for the height profile, so you can remove parts or the outer boundaries of your surface. In my case here, I decided to cut off 3 millimeters at each side because the sample was scanned is 100 millimeters long and 150 millimeters wide. So when I want to cut off 3 millimeters at each side, that's what I come up with. Another new value, so is the rotation angle. So the simple part here is that often if you scan a fracture surface with a 3D scanner, the scanner will not perfectly align it in a rectangular or in horizontal way. And therefore, in FSAT, there is a simple rotation pre-processing step where you can specify a rotation angle here, and the FSAT will rotate all data points by that angle so that it's perfectly aligned horizontally and vertically. The spacing is for the regular grid again, so this is here equal in both dimensions, and you have an first, start, and end parameter for the window or for the bandwidth size you're allowing for the fitting of the host exponent. Again, you should take a look at the single height profile analysis if you want to know more. Another new parameter here is the so-called angle step. FSAT will, for 2D surfaces, perform anisotropy analysis. And to do this, you can here specify with which step size in degree you want to perform this anisotropic analysis. So if you choose a smaller value, the more work FSAT has to do, so the calculation will take longer because there are more angles it will test on. If you do larger values, of course, there will be less analysis. In any way, FSAT will always perform in both dimensions, so in horizontal and in vertical direction. Again, this is pretty much everything you need to provide for the metadata, so we can simply execute this file. I specified to the beginning a file name where I want to store this metadata. It's called metadata surface. So now all I have to do is to provide this file name in the analyze sample script. So remove the old file name with the new one, and we execute the script. So you see there's way more output for the 2D surface than there has been for the 1D height profiles. So Again, as for the other steps as well, the generation of the metadata might be a repetitive process. So we can start with taking a look at the raw data. So this is really the data as you provided in the raw data file. So it's just points. You see, that's what I meant, is it's not from the scanner, not perfectly aligned horizontally, vertically. So we will just do a slight rotation by the parameters given. But so you see here, so I already tested the 2.6 degrees I'm providing in the metadata is something that varies very fine for this kind of sample. But of course, and you can now look at it, and if you're not happy with the result, you can change the metadata file. And you also see the problem I mean with the cutoff. So you see there are a couple of erroneous points at the borders, which are not perfectly well covered by the scanner. So when we set to 0, we want to cut off a few of those points here at the border. There's also one point that probably is not correctly covered. So just to remove those errors, we cut it. And then, as you already know from the 1E profile, you want to remove general trends. So you want to have everything to one common mean surface to remove general trends. That you can see here. It's just showing, okay, there is a few points up and above. But it's mainly to show that everything worked. And you can get, again, the interpolation on the uniform mesh, right? So now this makes much more sense. It's already leveled to 0, right? So we see a maximum difference of almost 12 millimeters. We can then also check the relative height. So this is then relative to the plane you've already seen before. And now this is a plot, for example, if you have an image of your rock fracture, or you have the rock fracture yourself available, where you can see, okay, is everything captured correctly? So this should be, like a positive height, and the blue ones areas here is related to a relative negative height to the general trend. So this is a good way here to compare that the scanner and also the processing was done correctly. So this is the plot that you already know quite well from the height profile. We'll now go also to the other plots that you have already done before. You remember that when you had looking at the single height profiles, that in the results table there was a lot of empty values because, well, you just have one profile. I said in the beginning, a 2D fracture surface is split in multiple profiles, exactly speaking, in as many profiles as there are based on the spacing you are providing of the regular mesh in the metadata. So we can do a lot of statistics, how things change over along the profile. So for example, we can take a look at the box plots for various amplitude parameters, and you can say how they vary, what the mean value is, and how the derivation across the surface is. Right? So you have these for a bunch of parameters. Yeah, we have that for amplitude. We have that for spatial change parameters here, so like angularity or things like this. So these are classical box plots here. We can also look at the spatial density parameters, like how many zero crossings, how many peak densities do we have, things like this. You can see if they are distributing widely across the surface, if it's very heterogeneous surface, if it's very homogeneous, right? That's things, information you can derive from those kind of plots. Right, and we have those all values I just showed you in 1 and 2 dimensions, which means in X and Y direction, so one's vertically and one's horizontal. Okay. The same thing as I did for the amplitude parameters, we can also do the statistics, of course, for the Hurst exponent, right? So we can see for all the profiles possible, how is the derivation, how's the change, what is minimum, what is maximum values. You can do this also for the JRC, for the joint roughness coefficient, which is a very, very common parameter. And you see that this one, for example, has a wide range of JRC values. So going from 5, which is rather smooth, up to 15, which is really, really rough. We have a mean value of 12, what again is quite okay for that kind of sandstone. That's what you would expect. But you see there is a strong variation. We also provide you with a few more insights. So for the Hurst exponent, you can check for the minimum and maximum value that was obtained during the analysis, how the fit looks like, right? You already knew from the other analysis that this linear relationship we're using here in the log-log plot breaks at some bandwidth. Again, here it was around 4. I decided that as this Wetherlin relationship breaks, you could also go like 4.2, 4.3, depending on the value you want to choose. Right. But both fits here look pretty good and match the expectation. For the JRC, we're providing you with the 2 profiles that show you the minimum and the maximum JRC value in this dimension. So you see, for example, we have here the smallest JRC of this profile was 4.9, and the highest one was 14.7. And you can just, for verification, that this is well done correctly, and you also for verification to see that the analysis itself makes sense, that it worked, that you did everything correctly for the metadata. I'm not going into detail this for the dimension, it just looks exactly the same. So you can do those again. There are, of course, also some statistics regarding the whole fracture surface, like the mean variance from the surface, from the interpolated plane, variance, standard derivation, skewness, and kurtosis of the distribution of the relative height. Here, and you get a histogram, which now you see in the height profile, it wasn't very Gaussian distribution here. It way more looks like a Gaussian distribution around 0. So there are slightly differences, which you might want to discuss. Things like this, also the box plots are especially helpful if you want to compare different kind of surfaces. What usually is the case because you want to study maybe some processes. And now you see the anisotropic analysis we performed, and there's also another folder just regarding those ones. So what we have here is just simply for the 3D measures value to show if the fit was correct or not. So these are a lot of plots because they are for different numbers of degrees in the step size you're providing. If you want to check on the surface parameter, surface roughness parameters and how it's calculated, I refer you, as for all our other roughness parameters, to our publication. Right? By just giving you here a few of examples, you see, okay, those fits are very well aligned. The trend is as it is supposed to be. So you can have trust in the determined parameter. If you want to take a look in the anisotropy, this is a lot of information. So that's why it was subfolder made just for this. Not all parameters can be used to calculate anisotropy, because, for example, every parameter that requires the whole surface to be calculated, like surface roughness, cannot be used, of course, for anisotropy. But everything that is based on a single profile, like we can do in an anisotropic analysis. And I would just again show the one for the JRC because it's the most simple one. And here you can say that it has some kind of anisotropy in this direction. You might want to try it again with a smaller step size. You see here this one in horizontal direction, it has the smallest values. So there gives you some idea about the anisotropy of your surface. And you can do this for all these kind of stuff, also for the Hurst exponent, where it's not that strong a difference, or for the zero crossing, right, where you see, okay, there is quite a strong anisotropy which you might want to discuss. It gives you ideas about flow field behavior and so on. Of course, we also provide you with the profiles in each direction that have been analyzed, also as points. So because those ones are extracted and interpolated from a 2D surface, so you might want to look into those profiles more directly if you have any questions, if you're not understanding the output, if you want to dig deeper into it, right? That's what we provide you with those informations. Right, and again, you will find all results in the CSV file if you need the quantitative analysis. But we have this also, again, in this workspace variable. You have, again, two parameters, so you will find the structure with the metadata information, as well as all the information that was generated on the way. So the homogeneous grid in X and Y direction, the raw data, the SAT, interpolated plane, the uniform heights, the relative height, the mean height, all those parameters. And now if you look into the results, you'll see those ones are way more filled now than for the single height profiles, as we have each calculation for each dimension, right? So there are a few which are based on the whole fracture surface, right? Those ones, of course, do not show any anisotropy. And then you have the other values. Let's go, for example, to the zero crossing, right? So zero crossing density. So you see, okay, there is a change. You can in fact calculate the porosity, and you will see what was the minimum and the maximum number that was obtained on a profile in each direction, and how then the anisotropic behavior between those ones was formed. All right, and you can do this for the JRC. You see here, okay, we have a very similar mean JRC in both directions. Well, there was slight difference between maximum and minimum JRC with the dimension 1, so the direction 1 being the slightly lower values, but has a higher mean JRC. So you can interpret that as a way as you like, but it is in agreement with the plot we have seen for the JRC in the anisotropy. I can reopen that one again. Right, so this directly correlates to this one. So we have this slide, right? Make sure here you're comparing this direction, so the horizontal, and so the vertical to the horizontal. So we see, yes, the mean value in the horizontal is a little bit lower than in the vertical direction. But also remember, this one is not mean values, but based on one single profile, so directly the one in the middle of each direction. Right? So this supports you in this anisotropic analysis. I hope this video was helpful for you to this video was helpful for you to understand how to process 2D fracture surfaces in FSAT and how to understand the generated output. The next video will deal with the analysis of 2 fracture surfaces, which again is quite similar, but it gives us, again, similar to the 2 height profiles, some information about the possible aperture distribution and then maybe flow field modeling and so on. Thank you very much.